In a 120/208 volt Y system, the neutral conductor should not be connected to the 480 volt delta to 120/208 volt Y transformer used in reverse to step up voltage. The neutral should also not be bonded to the transformer enclosure, or CAN. The question of whether the conductor, previously a number 4 wire, should be changed to a number 1 wire is not applicable, since the neutral should not be connected in this configuration. The breakdown of the number 4 wire was caused by a phase loss, which created an imbalance in the electrical system. This imbalance led to a significant increase in current flowing through the neutral conductor. Because the number 4 neutral conductor was undersized, it could not handle the increased current, leading to overheating and melting of the insulation and conductor. According to the National Electrical Code, NEC, each transformer on the secondary side, in this case the 480 volt to 380 volt transformer, should be bonded to the building steel from the transformer enclosure, or CAN. Let's delve deeper into the concepts of grounding and bonding, as they are crucial for electrical safety and proper system operation. Grounding refers to connecting the electrical system to the earth, providing a low impedance path for fault currents. This helps to quickly trip circuit breakers or blow fuses, preventing electrical shock hazards and equipment damage. Bonding, on the other hand, involves connecting non-current carrying metal parts of the electrical system together, such as transformer enclosures, metal conduits, and equipment frames. This creates an electrically continuous path, ensuring that all metal parts are at the same potential. In the described scenario, the improper bonding of the neutral conductor to the transformer enclosure created a hazardous situation. When a phase is lost, the unbalanced current seeks a return path, and if the neutral is improperly bonded, it can cause excessive current to flow through the grounding conductor, leading to overheating and potential fire hazards. The NEC provides specific guidelines for grounding and bonding electrical systems, including transformer installations. These guidelines are designed to minimize the risk of electrical shock and fire. It is essential to consult the NEC and follow its requirements when designing and installing electrical systems. Let's discuss the specific NEC articles that are relevant to this situation. NEC Article 250 covers grounding and bonding requirements. It provides detailed information on the types of grounding systems, grounding electrode requirements, and bonding methods. For transformer installations, NEC Article 450 provides specific requirements for transformer overcurrent protection, grounding, and ventilation. These articles should be carefully reviewed and followed to ensure safe and compliant installation. In the case of the 480 volt delta to 120/208 volt Y transformer used in reverse, it is important to understand that the transformer is being used as a step-up transformer. This means that the lower voltage winding, the 120/208 volt Y side, is being used as the primary winding, and the higher voltage winding, the 480 volt delta side, is being used as the secondary winding. When using a transformer in reverse, it is important to consider the voltage and current ratings of the windings. The transformer must be rated for the voltage and current that will be applied to the primary winding, and the secondary winding must be able to handle the voltage and current that will be supplied to the load. In this scenario, the 120/208 volt Y winding must be rated for the 150 amps that are being supplied from the fuse disconnect. The 480 volt delta winding must be able to supply the current required by the 380 volt printing press. It is also important to consider the impedance of the transformer. The impedance of a transformer is a measure of its opposition to the flow of alternating current. A higher impedance transformer will have a lower short circuit current, which can help to protect the electrical system from damage in the event of a fault. The NEC requires that transformers have a nameplate that provides information about the transformer's voltage, current, impedance, and other important ratings. This information should be used to ensure that the transformer is properly sized and protected. In addition to the NEC requirements, it is also important to follow the manufacturer's instructions for installing and operating the transformer. The manufacturer's instructions will provide specific information about the transformer's wiring, grounding, and overcurrent protection requirements. Let's consider the size of the conductors used in this installation. The number 1 wires that were used to feed the 120/208 volt wire side of the transformer from the 150 amp fuse disconnect may or may not be properly sized depending on the ampacity of the wire and the installation conditions. The NEC provides tables that specify the ampacity of different sizes of conductors. These tables take into account the type of insulation, the ambient temperature, and the number of conductors in a raceway or cable. It is important to consult these tables to ensure that the conductors are properly sized for the application. The number 4 wire that was used as the equipment grounding conductor was clearly undersized. The NEC requires that the equipment grounding conductor be sized according to the size of the overcurrent protection device. In this case, the overcurrent protection device was the 200 amp fuse disconnect, so the equipment grounding conductor should have been sized according to NEC table 250.122. This table specifies that for a 200 amp overcurrent protection device, the equipment grounding conductor should be at least a number 6 copper wire. It is important to note that the equipment grounding conductor must be properly connected to the transformer enclosure and to the grounding electrode system. This will ensure that the equipment grounding conductor provides a low impedance path for fault currents. Let's also consider the conduit that was used to run the conductors. The conduit appeared to have been overheating, as evidenced by the blackening of the connectors and the melting of the plastic bushings. This overheating was likely caused by the excessive current flowing through the grounding conductor. The NEC requires that conduits be properly sized to accommodate the conductors that they contain. The NEC also requires that conduits be properly supported and grounded. This will help to prevent overheating and ensure that the conduit provides a safe and reliable pathway for the conductors. In summary, the electrical outage and subsequent issues with the printing press were caused by a combination of factors, including the improper bonding of the neutral conductor, the undersized neutral conductor, and the improper grounding of the equipment. To prevent future problems, it is important to ensure that the electrical system is properly designed, installed, and maintained in accordance with the NEC and the manufacturer's instructions. This includes properly grounding and bonding the equipment, using properly sized conductors, and providing adequate overcurrent protection. In addition to these technical considerations, it is also important to consider the safety aspects of working with electricity. Electricity can be dangerous, and it is important to take precautions to protect yourself from electrical shock and other hazards. Always disconnect the power before working on electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as rubber gloves and safety glasses. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work. A qualified electrician will have the knowledge and experience to safely and properly install and maintain electrical systems. The NEC is a comprehensive set of standards that provides guidance in the safe installation and maintenance of electrical systems. It is important to consult the NEC and follow its requirements when working with electricity. By following these guidelines, you can help to prevent electrical accidents and ensure the safety of yourself and others. Let's talk more about the concept of bonding to building steel. Bonding to building steel provides an effective ground path because the steel structure is typically interconnected and grounded to the earth. This creates a large, low-impedance ground plane that helps to quickly dissipate fault currents. The NEC specifies the requirements for bonding to building steel in Article 250. It requires that the bonding connection be made to the building steel at a point that is accessible and that the bonding conductor be sized according to the size of the overcurrent protection device. It is important to ensure that the bonding connection is properly made and that the bonding conductor is securely fastened to the building steel. This will ensure that the bonding connection provides a reliable ground path. In addition to bonding to building steel, it is also important to bond other metal parts of the electrical system together, such as metal conduits, equipment frames, and enclosures. This creates an electrically continuous path that helps to prevent voltage differences between metal parts. Voltage differences between metal parts can create a shock hazard, so it is important to ensure that all metal parts are properly bonded together. The NEC specifies the requirements for bonding metal parts of the electrical system together in Article 250. It requires that the bonding connections be made with listed bonding connectors and that the bonding conductors be sized according to the size of the overcurrent protection device. It is important to ensure that the bonding connections are properly made and that the bonding conductors are securely fastened to the metal parts. This will ensure that the bonding connections provide a reliable electrical path. The scenario described in the question highlights the importance of understanding and following the NEC requirements for grounding and bonding. The improper grounding and bonding of the electrical system led to a hazardous situation that could have resulted in serious injury or property damage. By following the NEC requirements, you can help to prevent electrical accidents and ensure the safety of yourself and others. Let's delve into the details of how an imbalance caused by a single-phase loss leads to increased current in the neutral conductor in a 120/208 volt Y system. In a balanced three-phase Y system, the current in the neutral conductor is ideally zero. This is because the currents in the three phases are equal in magnitude and are 120 degrees apart. The vector sum of these three currents is zero, so there is no current flowing in the neutral conductor. However, when one phase is lost, the system becomes unbalanced. The currents in the remaining two phases are no longer equal in magnitude, and the vector sum of these two currents is no longer zero. This results in a current flowing in the neutral conductor. The magnitude of the current in the neutral conductor depends on the magnitude of the imbalance. The greater the imbalance, the greater the current in the neutral conductor. In the scenario described in the question, a loss of one phase created a significant imbalance in the system, resulting in a large current flowing in the neutral conductor. The undersized number 4 neutral conductor was unable to handle this increased current, leading to overheating and melting. It is important to note that the current in the neutral conductor can also be increased by other factors, such as nonlinear loads. Nonlinear loads, such as electronic devices and fluorescent lighting, draw current impulses rather than in a smooth sine wave. These pulse currents can create harmonic currents which can flow in the neutral conductor. The NEC requires that the neutral conductor be sized to handle the maximum expected neutral current, including the effects of nonlinear loads. In some cases, it may be necessary to increase the size of the neutral conductor to prevent overheating. The NEC provides guidance on sizing the neutral conductor in Article 220. It is important to consult this article and follow its requirements when designing and installing electrical systems. In addition to sizing the neutral conductor properly, it is also important to ensure that the neutral conductor is properly grounded. The NEC requires that the neutral conductor be grounded at the service entrance and at each separately derived system. This provides a low impedance path for fault currents and helps to prevent voltage differences between the neutral conductor and ground. It is also important to ensure that the neutral conductor is not used as an equipment grounding conductor. The NEC prohibits the use of the neutral conductor as an equipment grounding conductor in most cases. This is because the neutral conductor is a current-carrying conductor, and using it as an equipment grounding conductor can create a shock hazard. The equipment grounding conductor should be a separate conductor that is dedicated to providing a low impedance path for fault currents. In the scenario described in the question, the neutral conductor was improperly bonded to the transformer enclosure, which created a hazardous situation. This improper bonding allowed excessive current to flow through the equipment grounding conductor, leading to overheating and potential fire hazards. The NEC requires that the neutral conductor be isolated from the equipment grounding conductor, except at the service entrance and at each separately derived system. This will help to prevent excessive current from flowing through the equipment grounding conductor. The discussion highlights the importance of understanding the principles of three-phase power systems and the NEC requirements for grounding and bonding. By following these guidelines, you can help to ensure the safe and reliable operation of electrical systems. Finally, let's consider the specific requirements for bonding transformers to building steel. The NEC requires that transformers be bonded to building steel to provide a low impedance path for fault currents. This helps to quickly trip circuit breakers or blow fuses, preventing electrical shock hazards and equipment damage. The NEC specifies the requirements for bonding transformers to building steel in Article 250. It requires that the bonding connection be made to the building steel at a point that is accessible and that the bonding conductor be sized according to the size of the overcurrent protection device. It is important to ensure that the bonding connection is properly made and that the bonding conductor is securely fastened to the building steel. This will ensure that the bonding connection provides a reliable ground path. In addition to bonding the transformer enclosure to building steel, it is also important to bond other metal parts of the transformer together, such as the transformer core and the transformer windings. This creates an electrically continuous path that helps to prevent voltage differences between metal parts. Voltage differences between metal parts can create a shock hazard, so it is important to ensure that all metal parts are properly bonded together. The NEC specifies the requirements for bonding metal parts of the transformer together in Article 450. It requires that the bonding connections be made with listed bonding connectors and that the bonding conductors be sized according to the size of the overcurrent protection device. It is important to ensure that the bonding connections are properly made and that the bonding conductors are securely fastened to the metal parts. This will ensure that the bonding connections provide a reliable electrical path. In the scenario described in the question, the 480 volt to 380 volt transformer on the secondary side should have been bonded to the building steel. This would have provided a low impedance path for fault currents and would have helped to prevent the overheating of the equipment grounding conductor. By following the NEC requirements for bonding transformers to building steel, you can help to prevent electrical accidents and ensure the safety of yourself and others. The printing press being fed from a 45 kVA transformer at 380 volts requires careful consideration of conductor sizing and overcurrent protection. The primary side of the transformer, operating at 480 volts, will have a lower current than the secondary side at 380 volts for the same kVA rating. It is crucial to calculate the full load amps on both the primary and secondary sides to properly size the conductors and select appropriate overcurrent protection devices. For the 480 volt primary side, the full load amps can be estimated using the formula kVA times 1000 divided by the square root of 3 times the voltage, or 45 times 1000 divided by the square root of 3 times 480. Which equals approximately 54.1 amps. For the 380 volt secondary side, the full load amps can be estimated using the same formula, but with 380 volts, or 45 times 1000 divided by the square root of 3 times 380, which equals approximately 68.4 amps. These calculations provide a baseline for selecting conductors and overcurrent protection. The conductors must be sized to handle at least 125% of the calculated full load amps, as required by the NEC for continuous loads. This means the conductors on the 480 volt primary side should be rated for at least 67.6 amps, and the conductors on the 380 volt secondary side should be rated for at least 85.5 amps. Standard conductor sizes and their ampacities can be found in NEC Table 310.16, which provides ampacities for various conductor types and insulation ratings based on temperature. For example, if using copper conductors with THHN insulation rated at 90 degrees Celsius, a number 4 wire is typically rated for 70 amps in a 75 degrees Celsius column, which is common for termination temperature limitations, so a number 3 wire would be a better choice, which is usually rated for 85 amps in the 75 degrees Celsius column for the primary side. On the secondary side, a number 2 wire, typically rated for 95 amps in the 75 degrees Celsius column, would be suitable. Keep in mind that these are just examples, and the specific conductor size will depend on the specific installation conditions and the type of conductor used. Overcurrent protection for the transformer is also crucial. The NEC provides guidelines for transformer overcurrent protection in Article 450. The primary side overcurrent protection should be sized no higher than 125% of the transformer's primary current rating unless certain conditions are met that allow for a higher value. In this case, 125% of 54.1 amps is 67.6 amps, so a 70 amp fuse or circuit breaker would be appropriate. The secondary side of a current protection should be sized no higher than 125% of the transformer's secondary current rating, unless certain conditions are met. In this case, 125% of 68.4 amps is 85.5 amps, so a 90 amp fuse or circuit breaker would be appropriate. Again, these are just examples, and the specific overcurrent protection size will depend on the specific installation conditions and the type of overcurrent protection device used. It is also important to consider the voltage drop in the conductors. Voltage drop can reduce the performance of the printing press and can even damage the equipment. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. To minimize voltage drop, it may be necessary to increase the size of the conductors. The length of the conductors and the amount of current flowing through them will affect the voltage drop. Longer conductors and higher currents will result in greater voltage drop. By carefully considering conductor sizing, overcurrent protection, and voltage drop, you can ensure that the printing press is properly powered and protected. Remember to always consult the NEC and follow its requirements when designing and installing electrical systems. Furthermore, the connection of the neutral and grounding conductors together at the disconnect violates NEC Article 250.24, which requires the neutral conductor to be isolated from the equipment grounding conductor except at the service entrance. Bonding the neutral and ground together at the disconnect creates a parallel path for neutral current, which can flow through the equipment grounding conductor and cause it to overheat. This is what likely caused the melting of the insulation and the conductor in the original scenario. The equipment grounding conductor should be connected to the transformer enclosure and to the grounding electrode system, but it should not be connected to the neutral conductor. This will ensure that the equipment grounding conductor provides a low impedance path for fault currents without carrying normal neutral current. The grounding electrode system should consist of a grounding electrode, such as a ground rod, a metal water pipe, or a concrete encased electrode. The grounding electrode should be connected to the equipment grounding conductor and to the neutral conductor at the service entrance. This will provide a common reference point for the electrical system and will help to prevent voltage differences between the neutral conductor and ground. The size of the grounding electrode conductor should be determined according to NEC Table 250.66, which is based on the size of the service entrance conductors. The grounding electrode conductor should be sized to handle the maximum expected fault current. By following these guidelines, you can ensure that the electrical system is properly grounded and that the equipment grounding conductor is not carrying normal neutral current. It is also important to regularly inspect the electrical system to ensure that all connections are tight and that there are no signs of overheating or damage. Any problems should be corrected immediately to prevent potential hazards. Another aspect to consider is the potential for harmonic currents generated by the printing press. Electronic equipment, such as variable frequency drives and power supplies, can generate harmonic currents that can flow back into the electrical system. These harmonic currents can cause a variety of problems, including overheating of conductors, transformers, and other equipment. To mitigate the effects of harmonic currents, it may be necessary to install harmonic filters. Harmonic filters are designed to reduce the amplitude of harmonic currents and to prevent them from flowing back into the electrical system. The size and type of harmonic filter will depend on the specific characteristics of the harmonic currents generated by the printing press. A qualified electrician can perform a harmonic analysis to determine the appropriate type of harmonic filter for the application. In addition to installing harmonic filters, it is also important to properly size the neutral conductor to handle the increased neutral current caused by harmonic currents. The NEC requires that the neutral conductor be sized to handle the maximum expected neutral current, including the effects of harmonic currents. In some cases, it may be necessary to increase the size of the neutral conductor or to install a separate neutral conductor for each phase. Furthermore, using a K-rated transformer can help to mitigate the effects of harmonic currents. K-rated transformers are designed to withstand the heating effects of harmonic currents. They have a higher temperature rating than standard transformers and are less likely to overheat when subjected to harmonic currents. The K rating of a transformer indicates its ability to handle harmonic currents. A higher K rating indicates a greater ability to handle harmonic currents. When selecting a transformer for an application with harmonic currents, it is important to choose a transformer with an appropriate K rating. By considering the potential for harmonic currents and taking appropriate measures to mitigate their effects, you can help to ensure the reliable operation of the printing press and the electrical system. Remember to always consult the NEC and follow its requirements when designing and installing electrical systems. Finally, the selection of appropriate overcurrent protection devices is crucial for protecting the electrical system and the printing press from damage. Overcurrent protection devices, such as fuses and circuit breakers, are designed to interrupt the flow of current when it exceeds a predetermined level. This helps to prevent overheating, fires, and other hazards. The NEC provides guidelines for selecting overcurrent protection devices in Article 240. The overcurrent protection device should be sized to protect the conductors and equipment that it supplies. It should also be selected to have an appropriate interrupting rating. The interrupting rating is the maximum amount of current that the overcurrent protection device can safely interrupt. The interrupting rating should be higher than the maximum expected fault current at the point of installation. Fuses and circuit breakers have different characteristics and are suitable for different applications. Fuses are generally faster acting than circuit breakers, but they must be replaced after they interrupt a fault. Circuit breakers can be reset after they interrupt a fault, but they may not be as fast acting as fuses. The choice between fuses and circuit breakers will depend on the specific requirements of the application. It is important to select overcurrent protection devices that are listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or all. Listed and labeled overcurrent protection devices have been tested to meet safety standards and are more likely to perform as intended. In addition to selecting appropriate overcurrent protection devices, it is also important to properly install and maintain them. Overcurrent protection devices should be installed in a readily accessible location and should be properly labeled. They should also be periodically inspected to ensure that they are in good working order. By following these guidelines, you can help to ensure that the electrical system and the printing press are properly protected from overcurrents. In conclusion, the issues experienced were multifaceted, stemming from improper grounding and bonding practices, undersized conductors, potential harmonic current issues, and inadequate overcurrent protection. Adhering to the NEC and employing qualified electricians are paramount for ensuring a safe and reliable electrical system for the printing press. Title: Transformer Grounding and Bonding Explained. Description: Learn about transformer grounding, bonding, and NEC compliance. Discover causes of conductor failure after phase loss. Essential electrical safety information. Tags: Transformer, grounding, bonding, NEC, phase loss, electrical safety, conductor, overload, neutral, electrical code. Location. Narration: in a 120/208 volt Y system stepping up to 480 volts delta using a transformer in reverse, the neutral conductor from the supply should not be connected to the transformer. The neutral conductor should also not be bonded to the transformer enclosure. The breakdown of the number 4 wire used as a grounding conductor was likely caused by a phase loss, which created an imbalance in the electrical system. This imbalance led to an increased current flowing through the grounding conductor, which was undersized and therefore overheated. According to the National Electrical Code, NEC, each transformer on the secondary side should be bonded to the building steel from the transformer enclosure. Now let's elaborate on these key points. The purpose of grounding and bonding is to ensure electrical safety and provide a low impedance path for fault currents to return to the source, allowing overcurrent protection devices to operate and clear the fault quickly. The NEC provides detailed requirements for grounding and bonding in Article 250. First, the neutral conductor should not be connected to the transformer in this setup. The neutral is intended to carry and balance current in a Y system under normal conditions, but it should not be connected to the enclosure of a transformer stepping up voltage. This is because the transformer is acting as a separately derived system, and the grounding and bonding requirements are different from a service entrance. Second, the grounding conductor, which connects the transformer enclosure to ground, must be sized appropriately and should not carry continuous neutral current. The original scenario mentioned a number 4 wire, which was likely undersized. The size of the grounding conductor must be determined based on the size of the overcurrent protection device protecting the circuit, as specified in NEC Table 250.122. If a 200 amp overcurrent device is used, a larger grounding conductor, likely at least a number 6 copper, would be required, according to the NEC. Third, the phase loss caused an imbalance in the system. In a balanced 3-phase system, the currents in each phase are equal and 120 degrees apart. When one phase is lost, the currents in the remaining 2 phases increase, and the neutral, or in this case the grounding conductor due to the improper connection, becomes the return path for the unbalanced current. This can overload the conductor, causing it to overheat and melt. Fourth, the NEC requires bonding the transformer enclosure to the building steel. This provides a low impedance path for fault currents to return to the source, which helps to quickly clear faults and reduce the risk of electrical shock. The bonding conductor should be sized according to NEC Table 250.102, based on the size of the largest ungrounded conductor. In addition to these points, there are other factors to consider. The type of conduit used is important. EMT conduit should be properly installed and grounded to ensure electrical continuity. The connectors should be tight and the conduit should be supported properly. The melting of the plastic bushings indicates excessive heat, which could be caused by the overloaded grounding conductor or by improper installation of the conduit. The overcurrent protection devices should be sized correctly to protect the conductors and equipment. The 150 amp fuses in the 200 amp disconnect may have been too large, allowing the grounding conductor to overheat before the fuses blew. The overcurrent protection devices should be sized according to NEC Article 240, taking into account the ampacity of the conductors and the type of equipment being protected. It is also important to consider the voltage drop in the circuit. Excessive voltage drop can cause equipment to malfunction and can damage electrical components. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. The voltage drop can be calculated using the following formula: voltage drop equals 2 times the length of the conductor in feet times the current in amps times the impedance of the conductor in ohms per foot divided by 1000. Finally, it is important to have a qualified electrician inspect the electrical system and make any necessary repairs. The electrical work can be dangerous, and it is important to have someone who is knowledgeable and experienced perform the work. A qualified electrician can identify potential hazards and ensure that the electrical system is safe and reliable. Let's elaborate on the NEC articles mentioned earlier and provide more details about their requirements. NEC Article 250, grounding and bonding, is the cornerstone of electrical safety. It outlines the requirements for establishing a safe and effective ground fault current path, which is essential for the proper operation of overcurrent protection devices and for minimizing the risk of electrical shock. Some key sections within Article 250 include Section 250.24, which covers the grounding of separately derived systems. This section specifies how to ground transformers and other sources of power that are not directly connected to the service entrance. Section 250.122 provides the requirements for sizing equipment grounding conductors. The size of the equipment grounding conductor must be based on the size of the overcurrent protection device protecting the circuit, as mentioned earlier. Section 250.102 covers the requirements for bonding conductors. The size of the bonding conductor must be based on the size of the largest ungrounded conductor. NEC Article 450 Transformers provides specific requirements for the installation and protection of transformers. Some key sections within Article 450 include Section 450.3, which covers the overcurrent protection of transformers. This section specifies the maximum size of the overcurrent protection devices that can be used to protect transformers. Section 450.10 covers the grounding of transformers. This section specifies how to ground transformers and other sources of power that are not directly connected to the service entrance. NEC Article 240, Overcurrent Protection, provides the requirements for overcurrent protection devices such as fuses and circuit breakers. Some key sections within Article 240 include Section 240.4, which covers the protection of conductors. This section specifies the maximum size of the overcurrent protection device that can be used to protect conductors. Section 240.6 provides the standard ampere ratings for fuses and circuit breakers. Understanding these NEC articles and their requirements is essential for ensuring electrical safety and compliance. It is important to consult the NEC and follow its requirements when designing and installing electrical systems. Now let's discuss the potential causes of the insulation melting on the grounding conductor. Besides the undersized conductor carrying excessive current due to the phase loss and improper neutral bonding, other factors could have contributed to the problem. High resistance connections can cause localized heating. If the connections at the disconnect, the transformer enclosure, or the grounding electrode were loose or corroded, they could have created a high resistance point, leading to heat buildup and insulation damage. Over time, this heat can degrade the insulation and eventually cause it to melt. Another possibility is harmonic current. As mentioned earlier, electronic equipment can generate harmonic currents that can flow back into the electrical system. These harmonic currents can cause increased heating in conductors, transformers, and other equipment. If the printing press had significant harmonic current generation, it could have contributed to the overheating of the grounding conductor. In addition, the ambient temperature can affect the ampacity of conductors. The ampacity of a conductor is the maximum amount of current it can safely carry. The NEC ampacity tables are based on certain ambient temperatures. If the ambient temperature is higher than the temperature specified in the table, the ampacity of the conductor must be derated. This means that the conductor can carry less current safely. If the grounding conductor was installed in a high-temperature environment, its ampacity could have been reduced, making it more susceptible to overheating. Furthermore, the type of insulation used in the conductor can affect its ability to withstand heat. Some types of insulation are more heat-resistant than others. If the grounding conductor had a low-temperature insulation rating, it could have been more susceptible to damage from heat. In addition to these factors, physical damage to the insulation can also contribute to its melting. If the insulation was nicked, cut, or otherwise damaged during installation, it could have created a weak point where heat could concentrate and cause the insulation to melt. Finally, the age of the insulation can also play a role. Over time, insulation can degrade and become brittle, making it more susceptible to damage from heat and other factors. In summary, the melting of the insulation on the grounding conductor was likely caused by a combination of factors, including the undersized conductor, the phase loss, the improper neutral bonding, high resistance connections, harmonic currents, high ambient temperature, low temperature insulation rating, physical damage, and the age of the insulation. It is important to investigate all of these potential causes to determine the root cause of the problem and prevent it from happening again. Understanding the potential causes of electrical problems and following the NEC requirements for grounding, bonding, and overcurrent protection are essential for ensuring electrical safety and reliability. A thorough inspection of the electrical system by a qualified electrician is recommended to identify any potential hazards and ensure that the system is in compliance with the NEC.